Hey everybody, so here is our next video in Unit 2, which we're going to focus on a couple of different things in here that are pretty quick to go through. So we're going to focus on the polarity of molecules. We are going to look at bond length, bond order, and bond energy. And we're also going to look at how the bond length is affected by the atomic radius. So we're going to bring those trends back into our content again. So a lot of applications in chemistry can really come back to those periodic trends. So in Chem 1, we talked about how to determine whether a molecule is polar or not. And although a molecule can have polar bonds, the molecule itself can be nonpolar overall. And it has to do with how the bonds are distributed about the central atom, and also whether or not you have lone pairs on that central atom. We have to look at, is the charge distributed symmetrically around? So let's go ahead and define what is a dipole moment. And a dipole moment is another way of saying whether a molecule is polar or not. So if a molecule is polar, we say that it has a dipole moment. Dipole meaning two poles. So a positive side and a negative side. So a dipole moment is the separation of charge on a molecule. And this depends on the magnitude of the charge and the distance of separation. Our little Coulomb's law application in there. So it's the separation of charge on a molecule, and it depends on the magnitude of the charge and also the distance of that separation. So let's take a look at these three examples right here. I'm going to use a different color here to color over these Lewis dot structures. So in this case, I have water. If you might remember, water is in fact polar. Water has a dipole moment. So across this oxygen-hydrogen bond, oxygen's more electronegative. So there's a stronger attraction for electrons going towards your oxygen right here. Across this oxygen-hydrogen bond, the same thing. There's a stronger attraction for electrons towards that oxygen. Because both of these bonds have a pole going towards the top of this molecule, like this, we say that this molecule has a dipole moment, okay? There's a dipole moment here. So I always said in Chem 1, well, if it's got lone pairs, it's always going to be polar. And that's true. But the reason is really not so much to do with the lone pairs. It has to do with these two bonds right here. So you have two partial charges going in the same direction. That means that the overall polarity of this molecule is polar. That means my oxygen side of the molecule, because most of my electrons want to be situated around oxygen, this side of the molecule has a partial negative charge, whereas this side of the molecule has a partial positive charge. So water is a polar molecule because of that. Let's take a look at NH3. So I have a couple more bonds here. I have 3 bonds and a lone pair. So across this bond, I have a charge or a pull going towards nitrogen, because nitrogen's pretty electronegative. Same thing here, and same thing here. So in this case, I have an unequal pull across all 3 bonds. What does that do? It's concentrating those electrons right here around this nitrogen. So this nitrogen would have the partial negative charge. Partial negative. Notice how I have a much larger region up here where my partial negative charge is for oxygen, because both of them are basically going up to this whole area. Whereas my ammonia, it's really just this little section right here. That's my partial negative. And of course, all of these guys would be partially positive on this side of the molecule. So whether how electronegative the atoms within that bond are, but it also has to do with the relative magnitude of that charge. So in this case, because I have 2 lone pairs on oxygen, there's a much larger space where my electrons can hang out. Therefore, this particular molecule with the 2 lone pairs, so because I have 2 lone pairs, this has a greater dipole moment. Greater dipole moment. Which means this particular molecule would be a little bit more polar than this one right here. So NH3 is a little less polar. It has a weaker dipole moment. Weaker dipole moment. Okay. And it has to do with where those poles are going from, right? So in this case, I have 2 bonds. They're both going upwards. This one, these 2 are kind of canceling each other out in a sense. So therefore, you have a little less of a negative charge there. Both of these 2 molecules have a dipole moment. This third one, on the other hand, does not. So oxygen's a little bit more electronegative than carbon. So you're going to have a pull in each direction across this bond. My pull is going to be towards oxygen. And in this case, my pull is also going to be more towards oxygen. Because these poles cancel one another out, they're both going in opposite directions, and they're both the same strength because there is an oxygen on both sides. In this case, there is no dipole moment for CO2, and that is because those 2 forces cancel one another out. So this has no dipole moment, that last one there. And this is what we have to consider, is there an equal or an unequal distribution of charge or separation of charge, right? There is no separation of charge on that CO2 right here because oxygen's pulling equally on that carbon. Neither side of that is more negative than another. Here, if nitrogen's more electronegative and it's pulling across all 3 bonds, I have a concentration of electrons right here. Same thing here. If I have a pull going towards this direction, I have a big concentration of electrons right here. And that's what we have to consider when we look at polarity. Let's take a look at sample problem 10. The question itself looks kind of long, but the answer is not that long. Because the noble gases have a filled s and p valence orbitals, they were not expected to be chemically reactive. In fact, for many years, these elements were called the inert gases because of this supposed inability to form any compounds. However, in the early 1960s, several compounds of krypton, xenon, and radon were synthesized, and a team at the Argonne National Laboratory produced the stable, colorless compound xenon tetrafluoride. So, the question is predict its structure and whether it has a dipole moment. So just a little bit of background information about how some of these noble gases do in fact react. Granted, not very well, but they can react a little bit. First, in order to answer a question like this, we should draw the Lewis dot structure. So let's do that. Fluorine has 7 valence electrons, and there are 4 of them. So that means my structure has 28 electrons that come from these 4 fluorines. And I have 8 electrons from xenon. So my overall structure should have 36 electrons. So least electronegative is going to go in the middle. So I'm going to put xenon in the center. And I'm going to tack on these 4 fluorines. So I have 1, 2, 3, 4. Let's start to make a tabulated list of electrons. So I have 36 electrons, minus 1, 2, 3, 4 is 8 in the bonds. Leaves me 28. Let's go ahead and put our lone pairs of electrons on fluorines. So let's count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So I am left with 4 electrons, and which means we need 2 lone pairs on xenon. So there's my Lewis dot structure. And what we can do is consider, or in order to figure out whether this is polar or not, we should consider the shape of this molecule. So this particular molecule has xenon in the center, and that xenon is bonded to 4 other atoms. And xenon also has 2 lone pairs. So if we consider that the shape of this molecule, so we'll say its molecular geometry, is square planar. Square planar. So even though on paper we might have drawn it one way, we have to remember that it might not necessarily look like this in real life. Not that your drawings have to be accurate to how it really looks, but we do need to consider the shape. And the shape of this is square planar. So if I were to try to represent this drawing, trying to draw it out so it looks a little more lifelike, xenon would be in the center. I'd have lone pairs at the top and bottom. I'd have a fluorine going towards the back. So I'm going to draw those with dotted lines. And I'd have a fluorine coming out of the paper. You're going to see lots of lines like this in organic chemistry if you take that in college. It's called a wedge and dash. So I tried to draw these two coming towards us and these 2 fluorines going back in the paper. So I make a square. So let's get a different color here so we could see that. But here's our square shape right there. So now let's look at this to determine, is this polar or not? Does this have a dipole moment? And across each of these bonds right here, we're not considering the lone pairs, but here I have a pole in this direction toward fluorine. I have a pole in this direction towards fluorine. Same thing here and same thing here. There is an equal and opposite pull in all 4 directions of this xenon, right? Each fluorine, they're all 90 degrees apart from one another, if you consider, right, their bond angles. And they're across here, this is 180 degrees. This fluorine's pulling the same amount that this fluorine's pulling, and this fluorine is pulling the same amount this one is pulling. We don't have to consider the lone pairs. So when I said in Chem 1, okay, if it's got lone pairs, it's going to be polar. That was true back then, but now we have to consider the molecular geometry as well. So this particular molecule has no dipole moment. This is a non-polar molecule. So we do need to do quite a few things in order to figure out if it has a dipole moment. It's hard to figure it out just by looking at the formula. You should draw it out. And you should definitely try to figure out the shape, particularly the molecular geometry. Let's try this next example here. So sample problem 11. Predict the molecular structure of the sulfur dioxide molecule. So sulfur dioxide is SO2. And we want to know, or we want to draw rather, resonance structures if necessary. Is the molecule expected to have a dipole moment? So let's look. In this case, let's count up our electrons. Both sulfur and oxygen have 6 electrons. So I have 6 electrons times there's 3 of them. I have 18 electrons to place. So least electronegative is going to go in the middle. Tack my oxygens on there. 18 electrons minus 4 gives me 14 electrons left to place. So here's where you'll have to start considering formal charges to figure out what is the appropriate Lewis dot structure for this. So I did say in a previous video, all right, well, we know that oxygen wants to bond twice. So let's say I just do this to start off with. Okay. let's count. So 2, 4, 6, 8, 10, 12. So that's 12. Looks like I would need another lone pair on there. So if I draw it this way, there's 2 electrons left, and then I took off that, put a lone pair on here. So this has 18 electrons. Let's consider formal charges. So this oxygen has a formal charge of 0, as does this oxygen. Sulfur has 6 valence electrons, minus 4 bonds, minus 2 electrons, also has a formal charge of 0. Let's say you drew this like this. This still has 18 electrons, but, oops, I forgot a pair there. But my sulfur and oxygen have formal charges that are other than 0. In this case, oxygen has a formal charge of -1, and sulfur has a formal charge of +1. And remember, we like to use the shapes that have the overall less formal charge. So instead of +1 and -1 equaling 0, if all of these are 0, this is the preferred Lewis dot structure. So here's our structure for that. However, we do have to also consider the shape of this. This is not a linear structure, and even though it's drawn linear on paper, this sulfur has 3 areas of electrons that are surrounding it. So if I consider all of these, this double bond, and this lone pair being as far apart from one another as possible, it would look a little something like this. So the shape, or rather the electron pair geometry, would be trigonal, planar, right? And it's planar because this has 1, 2, 3 areas of electrons, but the molecular geometry is bent. So considering that, let's go ahead and determine, okay, well, who's more electronegative? Across this bond, oxygen's a little more electronegative, so I'm going to have a pull in that direction. And same thing here. I'm going to have a pull in that direction as well. So in this case, this is a polar molecule. This does have a dipole moment. And that's because right here, I have both of these charges going down in this direction. So this side of the molecule would have a partial positive charge, whereas both oxygens would have that partial negative charge. Even though over here, it seems as though this is linear and it's not going to have a dipole moment, we do have to consider the shapes of these molecules. And this is where this particular unit can start to get a little tricky for some people, because we do have so many things we have to think about. Let's go ahead and talk about just bond length, bond order, and bond energy. So this is not going to take us very long because I think it's pretty straightforward. Here is a comparison of the bond between 2 nitrogen atoms in a bunch of various different structures. So this first one is hydrazine. And we'll see right here, we have a single bond in between those nitrogens. So let's just highlight that. This is a single bond, okay? These types of bonds are going to be the weakest, but they're also going to be the longest. And notice how I did not draw this to scale. I couldn't find images that would show the length of them per se. But so that part's not drawn to scale, but this bond would be the longest of all of these examples right here, because single bonds are the weakest. There's only 1 pair of electrons that's holding them together. Our double bond right here, double bonds right there in the center, I have 2 pairs of electrons that are holding them together. Whereas if I have 3 pairs of electrons that are holding 2 nitrogen atoms together, there's 3 pairs of electrons. These are going to be the strongest, and they're also going to be the shortest type of bond. And the reason why they're the shortest, it has to do with orbital theory. right, which we're going to talk about in the last section here, valence bond theory. So you don't have to worry about the why are triple bonds the shortest. You really don't need to know. But if you are interested, we will start to get into that a little bit at the end of this section. I think it makes sense, though, that triple bonds are the strongest because you have 3 pairs of electrons that are holding them together, whereas here you have 1 pair of electrons that are holding them together. So, of course, if you start reinforcing the bond, it's going to get much stronger. And this is a nice segue into what's known as bond order. So bond order is a lot easier than it sounds. Let's get this going here. Bond order is just a very vaguely and simplistically, there's a lot more behind bond order, but we don't have to be that exact about it because we just need to get the general idea. I spelled vaguely wrong. Let's see. Is that better? I think that looks better. It is the number of pairs of electrons in a bond. And the higher the bond order leads to, the stronger bonds. I think this is pretty self-explanatory. Here's some examples down here. So if I have this ethane molecule, that's what this is called right here. I used to teach a little bit more organic chemistry, but there's just not enough time in Chem 2 anymore. There's like so many things I want to cover, and I'd rather prepare you guys a little bit more for AP and Chem 2 than that. So this is ethane. This particular structure, this carbon-carbon bond, that bond has a bond order of 1. And that's because there is only a single bond that is holding them together. If I compare that to ethene, so this is ethene, same prefix but different suffix at the end. This carbon-carbon bond has a bond order of 2, and that's because it is a double bond, right? So this is pretty straightforward. This last one, this ethine, which is what this is called, has a triple bond that are holding the carbons together. Therefore, this has a bond order of 3. Okay? Like I said, straightforward. So if I said to you, what's the bond order of this nitrogen-nitrogen bond? You would say 2. Okay? What's the bond order of this nitrogen-hydrogen bond? It's 1. Okay? It's just telling you, just another way of saying it's a double bond, a triple bond, or a single bond. Where it could start to get a little confusing, however, is when we start to look at resonance structures. So we want to consider what is the bond order of the nitrogen-oxygen bond in the nitrate ion. So the nitrate polyatomic molecule looks like this. So let's go ahead and draw that Lewis dot structure. I'm going to draw it, yeah, we'll draw it up here because then we could just rewrite it here so we could see the bond order stuff a little bit better. Let's see, 6 times 3 is 18, plus another 5 gives me 23. Have to add an electron, so this has 24 electrons total that I have to place. Let's put nitrogen in the middle. I'm going to tack on those oxygens. So there's 6. And looks like I have 18 to place. To save time, I'll just show you what this Lewis dot structure ends up looking like. You could, of course, double check your formal charges, but I'll tell you what they are. Looks like this. So, formal charge on this oxygen is 0. Formal charge on this nitrogen is +1. And formal charges here and here are -1. So, therefore, the overall sum of those formal charges is -1, which is what we have. Let's go ahead and redraw this a little bit nicer if we can. So, I have oxygen, nitrogen, oxygen. if I want to know what's the bond order between the nitrogen-oxygen bond, we have to consider all of the resonance structures of this. Because if we remember back to resonance structures on a previous page, no one of those resonance structures really exists. We have a combination of these resonance structures. So we have to take that into consideration when we're trying to find out what's the bond order, because the bond order is not one, because when I combine all of these, it's a little bit more than a double bond or a single bond, but it's also not quite a double bond. And it's also not directly in the middle, so we'll talk about what that bond order is going to be. Let's draw the resonance structures first. So here's one resonance structure. Let's draw the second one. So I'm going to move this double bond and I'm going to put it down below here. So I'm just changing the location of that double bond. There it is. Let's get the last one here. So I'll change that last location. Double bond now should be here. Okay. So remember, not one of these exists. In real life, we have a combination of all of these. Let's take a look at this bond in all of them. So I'm going to look at this nitrogen-oxygen bond, that one, and this one. There are 3 resonance structures of this. 2 out of 3 times, this bond is a single bond. And 1 out of 3 times, this bond is a double bond. The way to calculate the average bond order is you're going to do exactly what it is. You're going to calculate the average. In this first structure, the bond order is 1. So I'll say BO equals 1. Here, that same nitrogen-oxygen bond has a bond order of 1. And in this last structure, that has a bond order of 2. So if I want to know the average bond order, I'm going to take all of these and add them up. So 1 plus 1 plus 2. And I'm going to divide by how many resonance structures there are. And there are 3 resonance structures. You get 4 out of 3, which is a bond order of 1.33. Okay? This bond is not quite a single bond, but it's not quite a double bond. The bond order is closer to that of 1, however, because more than half the time, 2 out of 3 times, that bond is a single bond. Okay? So your bond order is just a little bit higher than 1. It's a little bit stronger than a single bond, but not quite a double bond. Okay? Because we have to remember all of these resonance structures will exist. Very interesting topic to consider, but that's how you would figure that out. Let's talk about this last section here quickly, and we're bringing it back to trends, right? So trends comes back to haunt us quite a bit throughout the course. So effect of atomic radius on bond length. So let's consider this trend right here. Bond length is proportional to atomic radius. So if I have diatomic fluorine, that bond between that fluorine is 143 picometers. If I consider diatomic chlorine, that bond length is 199 picometers. Bromine, which is underneath those, has when they're bonded to one another, has a bond length of 228 picometers, and iodine is the largest. Why, as I go down a group, do the bond lengths get longer? It makes sense. Is because iodine is the largest atom. Iodine has 5 shells that surround it, whereas fluorine has only 2 shells. So because fluorine has 2 shells, those nuclei can get closer to one another. Whereas if iodine has 5 shells, those nuclei cannot get as close to one another. So therefore, the bond length is going to be longer. It's very straightforward, right? I mean, it makes a lot of sense. The larger the atom, the farther away they can get from one another. So iodine has the longest bond because it's the largest atom. This is a result of iodine having the most electron shells surrounding its nucleus. Done. You're going to see, and I come across these a lot, lots of questions like this, like just like this, where you have to, predict the bond's length given a whole bunch of elements. But you're going to see that there's a trend in there somewhere. And this is why the trends will always come back, is because those trends can describe just about anything. And then this bond length can describe reactivity of these elements. How does reactivity increase or decrease going down a group? This is what makes chemistry so exciting, is because it all comes together in the end. When I started teaching, I didn't really think about how all this stuff came together. And now that I'm teaching it and I'm in it and I'm learning more every day, I'm like, oh my gosh, it all comes back together. I had such an easier time in some of my grad school classes because I knew periodic trends from teaching them. So knowing these trends really, really helps. And I know nobody likes the trends, but it does help quite a bit. That's where we're going to stop for today. As always, if you have any questions, please let me know. Otherwise, I'm not going to make a video for the last section, actually, because that gets a little crazy, the last video. So I'm going to do it in class. But otherwise, I will see you in the next unit for Unit 3, which is, it's a doozy. There's a lot of stuff in there all about intermolecular forces and properties. So I will see you then. Bye.